Hello everyone. Um, Welcome to this. I think this is the first talk we're doing in the actual stage. I don't know if Baki already has done a talk here, but if not, then this is the first one. I'm going to be talking about binary representations, which will cover everything from the very basic principles of binary numbers, the way they work as a number system, and we'll eventually build up to things like ASCII and UTF-8 encoding, and we'll also cover a bit of the floating point numbers as well. So to start off, should start with we should start with the absolute basic. I expect most of you to already understand how binary numbers work, but we'll go over it anyway, so we're all on the same page. So in our daily lives, we use the decimal number system for counting and for writing down numbers, which was originally invented because we have 10 fingers, which is the most straightforward way to count things. There have been other uh, quote unquote superior number systems that have been proposed. Those are not necessarily worse. They are actually better in a lot of ways, but they are just very hard to integrate. So we have the number system has basically stuck for the last couple of 100 years. There's one problem with decimal, and that is that it is very hard to represent in a electronic circuit, because if you were to use something like voltages or amps or something like that, um, you'll have to deal with things like signal integrity, and you also need components that are very complicated and are also very expensive. So all in all, it is not very. It's not a practical way to represent numbers in electronics. You want to keep the signal as simple as possible, and the simplest way to uh, transfer information from over an electronic wire is by using on and off states, which leads us to the binary counting system, which is a number system with only two digits, 0 and 1. And because it has two digits, we can represent each digit with an on and off state, um, which is very useful in electronics. And it is, and there are a lot of components like here. We have transistors in large supply, which makes this a very useful tool when building computers, and it forms the basics, and it has become the basis of all computers in the modern age because of this. So how do we count in binary? Because you might have the question of how does a number system different from ours work? So in decimal, we use different positions in a number to represent different values. So we have the ones place and the tens place and the 100s place, and we'll use different digits on these places and then add those together. And more generally, each place represents a power of 10. And the same thing goes for binary, but instead of powers of 10, we are now using powers of 2, where we have one place, we have the ones place and the twos place and the fours place and so on. And this makes sense because where decimal has 10 digits, binary only has 2, so we use powers of 2 instead of 10. So let's go through an example of the conversion to binary. I have two beautiful, very arbitrarily chosen numbers. So let's get rid of this. And then let's write down our numbers. We've got 69. Let's convert 69 to binary. So to start off with a conversion to binary, we want to find the biggest the biggest binary, the biggest power of 2 that fits inside our number. In this case, this is going to be 64. And we're going to subtract that. Or I should actually write down which power of 2 this is. This is equal to 2 to the power of 6. So we're going to subtract these, and 69 minus 64 is going to be 5. And then we do the same thing again. We find the biggest power of 2, which fits in 5, which is going to be 4, which is 2 to the power of 2. And then we'll end up with 1. And the largest power of 2 that fits in this is just going to be 1, which is 2 to the power of 0. And then we have 0 left. And these powers of 2 we've written down here, those are the binary places where there should be a 1 in our number. So we're going to have a 1 in the zeros place, then 0, then a 1 in the fourth place, then a 0, another 0, and then there is 0, 1, 2, 3, 4. And then there will be a 1 here. And this is going to be our binary representation of our number. The other way around, suppose we have a different number. So let's go ahead and look at this thing with 1101001000. Let's see if I can remember that. After I remove all of this. So we have what's the first part? 1101 and then 00100. So if we want to convert the other way around, that's a bit simpler. We just find the power of 2 that corresponds to each one, and then we add those together. So we're going to go to the power of 0, to the power of 1, to the power of 2. So we should have a 4. Let me use a different color for that. A 4. Then this would be a 16, a 32. Not a 64, 128, and 255. And we're going to add those together. So we're going to have 255 plus 256, sorry. 256, 128, 32, and 4. Add those together. We're going to have, well, we already know the answer. If you were to go through this addition, you would end up with 420. And that's how we convert from binary to decimal. You already have noticed that numbers in binary need more bits to be written down than we need digits in decimal. And this makes sense because every bit contains 5 times less information than a digit. So of course we will need to represent 2 big numbers. We're going to need more binary bits than we need the decimal digits. Okay. Addition. How do we add numbers in binary? Because we can now write them down, we can convert them, but we need a way to actually do math on them. And luckily, math in binary is surprisingly easier than it is in decimal. And this is generally the case for number systems with lower bases. They provide, because each digit only contains very little information, the actual arithmetic is a lot easier. And this is also why other number systems like base 6 have been proposed to be used in our daily lives. But the process of transferring to a number system like that is just very complicated, so it has never actually happened. and it's probably not going to happen anytime in the future. Computers add numbers using vertical addition, like we do with numbers that are too big to add in our heads. So we just put the numbers under each other and then go through each digit one by one until we have added the whole numbers together. And because binary is so simple, we only have to consider 4 addition cases for each digit, which are 0 plus 0, which is just going to be 0, 0 plus 1 in any order, which is also going to be 1, then 1 plus 1 in any order if you consider the carry, which is just going to be 2 or 1, 0, and then 1, 1 plus a carried 1 from the previous digit, which is going to be 1, 1. There is never going to be 2 carried bits because there is just not a case here that produces 2 carried bits unless you have a case that has 2 carried bits to begin with, which can then never be created. So these are the only 4 addition cases we have. And that is very easy to implement. I'm not going to go into the whole logic gate and circuitry of implementing this. I'm just going to explain the concept because the whole underlying circuitry is a bit irrelevant to what I want to explain here. So let's add these numbers. I'm going to copy this. I'm going to open a IDE. And let's just make a new file. So what are we going to do? We are going to add these 2 numbers together. So we have 1 plus 0. This, of course, is just going to be 1. We have 0 plus 0, which of course is just 0. We have 1 plus 1, which is of course going to be 2, which means we have a 0 here, and we're going to carry the 1 over to this place. Then we have a 1 plus 0 plus 0, which is just 1. 0 plus 0, which is just 0. Then 0 plus 1, which is just 1. Then 1 plus 0, which is just 1. And then 2 times a simple 1. And there we go. And this should be equal to 420 plus 69. So let's go and see if that is the case. If we go to a binary converter. Again, I very much encourage you to just go to one of these conversion sites because doing the conversion from binary to decimal by hand is good practice, but you won't need it most of the time. We need the other way around. This should be 489, which is indeed equal to 420 plus 69. This also allows us to do multiplication, which is even simpler when you know addition, because we only have multiples of 1 or 0. If you were to do a vertical multiplication on paper, you would take the digit, move it to the same digit place as the other digit you're working with right now, and then multiply it by the digits you're working with. So for example, if you have 25 times 36, you would go through each digit of the 36 and then move 25 to that digit's place and multiply it with the digit. But because we only have multiples of 1 or 0, which are both trivial cases of multiplication, this becomes very easy, which I will show right now. I'll do this on paper because this is a little bit of an easier example. I wish this was faster. I'm not used to working with Excel. I just kind of picked something which works for now. So let's just grab, what did I write down here? 1011 and 101. 101. Multiply those together. So again, what we do is we go through each digit of 101 and then shift 1011 to that digit place and multiply it with the digits. So we're gonna have a 1 here, which means we will just add 1, 0, 1, 1 in this spot. We have a 0 here, so we're going to skip over this altogether and move to the next one, which is here. And we're gonna add the number again here in this place. And then add those together. So you see that multiplication is a lot more straightforward because we only have these two trivial cases of multiplication. And we just add those together, which is just going to be this. And there you go. And this was 11 times 5, which should be 55. Let's see if that's true. This is a 1 plus 2 is 3, this is 7. This becomes 23. 23 plus 32 is 55, indeed. So that's multiplication. But in practice, unlike when we are working with digits on with our pen and paper, we only are limited to we only have a limited number of bits we can use. It's a bit like a rotary display, like you see on a number lock or something like that. And when you exceed the maximum number you can represent within your number range, you get what's called an overflow, which is basically what happens when your rotary display reaches 9999 and so on, and then it will flip back to 0. And this is most of the time undesirable behavior. It's basically the source of a lot of bugs you see in also a lot in games. If you're looking at Minecraft, has a lot of overflow related bugs as far as I know in older versions. But there is one specific use case where overflowing becomes actually intentional behavior, which is when subtracting numbers or representing negative numbers. So if you have been wondering about how we should go about using writing down negative numbers and doing subtractions, this is how we do it. So suppose we have a 4-bit number, or we are working with 4-bit numbers in general, which means they will overflow after. Oh wait, this should actually be a 3-bit number. Let me just correct that. I'll just say 3 bits. And then start the slides again. So suppose we're working with a 3-bit number, which means our numbers will overflow after reaching 111 in binary. And we want to add two numbers together and say that the addition of x plus y causes an overflow to occur. This means our result will not be x plus y, but will instead be x plus y minus 1000, because the decimal place after that gets discarded because we are only working with 3 bits. We can actually rewrite this result to be x minus 1000 minus y. And if we now let c be this part within the brackets, we can rewrite this as x minus c, which already brings us closer to what is potentially a subtraction. And we have only, remember, we were initially just adding two numbers together, but we are getting a different number that is potentially smaller than x originally was. So we have almost done a subtraction, but we still need to find this number 1000 minus y. And this is where binary actually has a very interesting property which we can use, which no other positional number system of any other base has. And that is when we are flipping the bits of a number, we are doing the same as calculating 1111 and so on minus x. You can try figure this out for yourself why this is. It is basically the same as if you subtract 99999 if you do a subtraction like 99999 minus x for a decimal number, you can imagine that you are switching every digit for a counterpart digit. But because we only have 2 digits here, this conversion is just the same as a bit flip. So if we want to subtract 2 numbers, all we need to do is start with x, then add the inverse of y, and then add 1, because remember we had to find 1000 minus y, but this bit flip will give us 111 minus y in this case. So we need to add 1 in order to get the actual number we need. So how do we define negative numbers in this case? Because we might be able to do subtractions right now, but we have no concrete way of, or like the standardized way of saying this number is negative and this number is not. And the easiest way to do this is, well, if you were to look at our number range right now, it seems like numbers that are above the halfway point act more like negative numbers in addition, whereas numbers that are not are acting more like positive numbers. So it seems like if we just split our range in the middle and say everything above it is negative and everything below it is positive, we get pretty close to a representation that works with our subtraction method. So suppose we take the number 1000 again, which was, so we're working with a 4-bit range now, but it's the same thing. This number is equal to 8, but in this same number system, it could also be seen as negative 8. Because if you were to add this to a number, it's basically like subtracting 8 in a sense. So we can actually turn this into the following. Numbers above 1000 are interpreted as negative, and then the negative number they represent is 8 minus the bit representation of the remaining bits after that one. So that's how we do negative numbers. And our first bit, if you haven't noticed, is actually becoming a flag for when a number is negative. So when its first bit is 0, we know that for a fact that our number we're working with is positive, and when it's 1, we know it's negative, which is a very useful property, which a lot of which processors actually use a lot in their circuitry. They'll just check for the first bit to see whenever a number is negative or not. These are also called signed numbers, which and the numbers we were working with previously are referred to as unsigned. With our signed numbers, we actually introduce another concept which is called underflowing. And like underflowing, numbers can basically roll from the positive to the negative range, or vice versa. So with unsigned numbers, we only had overflow because we don't have a negative number thing. We only have only addition is defined in unsigned numbers. Basically, subtraction is like it's it's still subtraction is still defined, but it is still called overflow in that case. With signed numbers, we have both underflow and overflow, where overflow occurs at the halfway point when adding. So that happens when we are adding 2 numbers that are above the halfway, that will give a positive number above the halfway point, which will be interpreted as negative when it is actually not. And we have underflow the other way around, when we have 2 very negative numbers that will cause the result to not overflow enough in order to get back into the negative range, which will give us a positive result when the result should actually be negative. This is a bit hard to comprehend, but if you were to draw the range of your number in a circle and then try to do like actually let's just do that. Let's just do that. Let's just remove this again. And let's draw a big circle. Cool. We're gonna have a this is gonna be 0. This is gonna be 1 0 0 0, and that's like, this is our negative range and this is our positive range. So if we have two very positive numbers, like for example here and here, if you add those numbers, it's like adding the length of this arc over here and adding them to each other, and that will be your new number. We are going to get like a number that's like over here or something, right? Which is in the negative range, which is not correct because we just added two positive numbers. So this number should not be negative. And this is what is referred to as an overflow. We are overflowing over this halfway point. Whereas if we had with an underflow, it's kind of the opposite. We want an overflow to happen, but it doesn't happen. So when we have if we have two very negative numbers, which remember is they go the other direction, so that is going to be numbers like here, and then another number like right here. The result, if we add two negative numbers, the number should actually be more negative, but our result is going to end up somewhere like over here, which is not where it should be because this is the positive range. So we just added two negative numbers and ended up with a positive number. And that's because this number should have actually overflowed into the negative range, but it didn't because these numbers are too negative for that to happen. So like this rotation was not sufficient to go back over this line, which means we now have ended up with a positive result when we shouldn't. So let's go into we can also look into other operations. With these operations which I just described, you can do things like integer division. We can square numbers using multiplication. We can do the modulo operation, all the stuff like that. I won't be explaining that because it's not really part of the thing I want to explain. But you can look into those if you're interested. So now that we have done that, we should define a few standards for integers and most importantly integer sizes. We use the following naming convention for this, which works like this. We have int, which is part of her name basically all the time, which is sometimes prefixed with an u to indicate that it is unsigned, and it is followed by the number of bits that are part that the integer holds, which is either 8, 16, 32, or 64. 128 is also sometimes a thing, but it is basically never used for... it isn't a thing on consumer platforms, basically. And yeah, it indicates when a number is unsigned or not. So a uint8 would be an unsigned 8-bit number, and a int32 would be a signed 32-bit number, and so on. And we can calculate the range of each of these numbers pretty easily. We just get the number of all ones for unsigned numbers and calculate what that number equals, and that's the biggest number you can represent. So in this case, if we have a 8-bit number, we just get 1, 1, 1, 1, 1, 1. We get just 8 times 1, and then calculate the value, which is just gonna be the 2 to the number of bits minus 1. That's a general rule which applies for all numbers. If you have 1, 1, 1, 1, 1, 1, 1, 1, that's just 2 to the 8 minus 1, which is 255. For signed numbers, we just get the smallest negative number and the largest positive number. And the largest positive number is actually a bit smaller in magnitude than the smallest negative number, due to the way we are doing subtraction. But if we are working with numbers in the scale of, if you're working with 32-bit numbers, that's a difference of 1 on the scale of 2 billion, which is basically irrelevant. So it isn't really a big deal. So our range would start at 1 0 0 0 0 and it would end at 0 1 1 1 1 1, which is minus 2 to the b minus 1 and 2 to the b minus 1 minus 1 respectively. So a 8-bit number, signed 8-bit number, would go from minus 128 up to 127. There are a few numbers like this that you actually want to know by heart when you're working with computers, and those are the following. You want to know the limits of the unsigned 8-bit numbers, or for basically all bytes, which is 0 to 255. You want the signed version of that as well, which is minus 128 to plus 127, or just remember one of the two and you will know. Like if you see a number that is close to that, you know that it has those are numbers you want to remember, because they might indicate an overflow or underflow happening when it shouldn't, and that's pretty useful information. And it's also useful for analyzing or reverse engineering software. Unsigned 16-bit numbers limits are also very useful to know, because they happen on older architectures a lot. So like 65,535 or about 64K, which if you don't feel like remembering that, then these two are common on all modern systems basically. The 32-bit integer limit, which ranges from minus 2.6 billion to 2.6 billion. If you feel like remembering the whole thing, go ahead, but that's basically not necessary, because overflows never happen at the point where they overflow. They always go a bit beyond it or a bit back. So if you have a problem and encounter one of these numbers and they are close to 2.6 or 2.5 billion, you know something has overflown when it shouldn't. And for the 64-bit, it's going to be minus 9.2 quintillion, and in both directions. We often also use the following names when referring to certain bit sizes. For 8 bits, we usually call it a byte or a char. 16 bits, we call it a word or a short. For 32 bits, a double word or d-word, and a integer, and like an integer written like int, and then 64 bits we call it a q word, quad word, or a long. Now the right side names are used in C, in the C-like languages, for the built-in types. In C and C++, those are not always gonna refer to the same sizes. They are actually dependent on the platform you're building for. A integer, can be anywhere from 16 bits up to 32 bits, and a long can be anywhere from 32 bits up to 64 bits. Which so if you are working with numbers where the size of the bits matter, you actually want to use the built-in STD, or you want to use a standard library of STD int types, which are concrete in the number of bits they use. One last thing we want to cover before we move on to ASCII and the other stuff is hexadecimal notation. If you have not yet noticed, writing down the bits for numbers with 32 bits is very inconvenient and very hard to read. So we actually invented a number system to make, or actually came up with a number system to make this a bit more easy, which is hexadecimal. Hexadecimal is base 16, and it is 16 for a reason, because it is made in such a way that when you have two hex digits, they will collectively represent exactly 1 byte. They will have 255, they can together represent 255 numbers, just like a byte does, which makes it very useful when you want to list a number of bytes, because you can just represent each byte with 2 digits without having any stuff to which you don't use. If you're using a decimal system, you have 0 to 255, so you're not making use of the entire number system. And conversion between binary and hexadecimal is also a lot easier, because you can just do the conversion for the first digit and do the conversion for the second digit and just stick those two together, and you'll have the actual binary number, which doesn't work in decimal, obviously. Okay, so we've just looked at numbers, but how would we go about representing other data? How would we represent stuff like, for example, text? And this is actually, we can actually apply a basic principle in computer science, and that is that any data, it doesn't matter what it is. If you're creative enough, you can represent any kind of data with numbers in some way or another. By either using indexing or some other principle, you can basically turn every single piece of data, how complicated it might be, you can turn it into some collection of numbers. So for text, let's just try and give every character a certain number. Just make a lookup table for number 1 corresponds to the letter A, something like that. And then we can make a text using a list of numbers, basically. So ASCII gives each character 1 byte, which means we can represent 256 different characters in theory. But only 128 of these are actually used, because the original ASCII specification asks for 7 bits and not 8. But using the rise of the whole computers, then it got because computers worked with 8 bits in their memory and stuff like that. It's basically just 8 bits with one bit to spare. This reason is therefore also not related to signed numbers. It just was that way before computers were invented, because ASCII was already used for I think it was already used for telegraph systems. I'm not sure about that, but it might have been. So this is what the ASCII, the 128 ASCII codes are. So you have a lot of, you will notice there are a lot of weird ones up here, but we'll cover those in a moment. Then we have a few of their symbols. You'll also notice that we have the 0 to 9 age conveniently lined up here. And this is so we can just subtract 48 from our number, and if it is within 0 to 9, we already have a digit to ASCII conversion, which is very useful. And then here the same goes for the alphabet. We have them lined up like this, so we can just subtract 64 and get the index of the letter in the alphabet. And here subtract 96 and get the index of the number in the alphabet, which is very useful as well. And then here on the end we have like the delete character, which is a bit irrelevant. So as you have might have noticed, we have a few things here that are called control characters. These were initially used for devices like printers. So if you would have like a printer that was connected with a like printer parallel cable, stuff like that, and it would send literal ASCII codes to your printer, which would say things like go and pull the paper 1 line further and go print there. And that's where the control characters were for. But because we no longer use that technique for instructing printers, because printers can now print images and stuff like that, which is way more complicated than anything ASCII can represent. A lot of these characters actually have become obsolete, but we still use these 10 ones, which are the null character for which is mostly used to terminate strings. Some strings just work with a length of the string at the beginning, but there are still a lot of systems which use this null terminating string, which is why this is still pretty relevant today. We have the bell character, which is used for the terminal alert. So your terminal would, if you were to print this character to the terminal, your terminal would make a sound to alert the user, which is also pretty commonly used. We have the backspace character. I don't personally use this a lot. I cannot really come up with a use case right from the top of my head, but there are some niche use cases where this is used. we have the horizontal tab, which is to do a horizontal tab in the to just move the cursor basically in a horizontal manner. We have the line feed, which is basically a new line character. So you will probably have used this once or twice at least to add a new line to your string, for example. And this is actually one of these ASCII control characters. We have the vertical tab, which this is actually an error. This should be /v, so just ignore that for now. That this is not correct. But this should be /v. But this one is very this is one is very rarely used, but it is still used sometimes. We have I don't know which one this was. What was this again? See, they are like still relevant today, but that doesn't mean they are often used. Form feeds, which was used to eject paper to the top of the next page. Oh yeah, it was used to clear the screen. Some people still use this to clear the screen, but most people will just do import like a library that gives you access to the shell, and then you can just clear the screen with that. So that's that. We then have carriage return, which is used on Windows together with line feeds to do a new line, which is also the root of all problems with conversions, with text conversion from Windows to Linux or whatever. Because that stuff just doesn't match up, and then you'll get like lines that like double new lines and stuff like that. Then we have sub, which I don't know what that is. Sub is a end of file code in Windows. And then of course you have the escape character, which is used for all the ANSI escape codes. You'll already noticed there's an issue with ASCII, and that is that 255 characters is not a lot of characters. If you look at different languages, you will notice Japanese, for example, has 142 kana, which is already half of our range, which we are already using half of our range. So that we wouldn't be able to include Japanese characters into our current ASCII system. And Chinese has 6,000 up to sometimes 50,000, depending on the dictionary you use, Chinese characters. So we wouldn't be able to even put a 10th or a 20th of that range in our system. And then we also have like less common symbols, other languages which I have not listed here, emojis. So how are we even supposed to begin with including those in our current system? Well, in some regions, because this was a actual issue, and because computers were not invented by one person, there were different systems with 1 byte encoding or with sometimes multi-byte encoding, which didn't match up with each other. And this is the cause for a concept called mojibake from Japanese, where a text encoded with one standard gets encoded with the wrong standard, and you get basically gibberish that comes out, which looks like this. And this is, of course, not something you want. You want something which is universally applicable, which includes all languages, and hopefully is still a little bit fast. So the easiest solution, of course, is to just add more bits, which is what UTF-32 does. It just gives every character 4 bytes, and now we can represent over 4 billion characters. Problem solved. Because the Unicode specs only ask for about 1 million characters, of which only 100,000 are in use right now. So we are basically good to go now. But with that said, our text now also takes up 4 times as much space, which is not a good thing if you care about storage space. And our UTF-32 standard is also not backwards compatible with the existing ASCII, which will cause mojibake when the thing is misinterpreted. So there are a lot of problems here that need to be addressed. First of all, we need to make common characters like the English alphabet take up less space, because if you would look at the codes for those characters, they will just be 1 byte for that character, which would be the same as ASCII, and then they would be preceded by what is basically 3 0 bytes. And that will be the case for basically every character you see right now on screen. Each character you see right now on this page would take up 3 additional bytes, which are all just 0, which is very wasteful. So UTF-16 helps to remedy this by, first of all, restricting the number of bytes each character gets to 2. Which gives us, in theory, 65,000 characters. But we can actually use a clever trick to increase this number, which is surrogate, which was called by the Wikipedia page, they call it surrogate pairs, which is a bit confusing, but basically it's a smart way of making an exception to the rule. So what we do is we take a range in our 16-bit numbers and exclude it from being used by 2-byte characters. So we get our in this specific case, we take the range D800 to DFFF and remove it from our character range. So our characters won't be using this specific range. We instead dedicate this to be used in pairs. So we can now define 4-byte characters by combining 2 numbers within this range. And each number will then have a 6-bit prefix, which is gonna be this D something something. And it will then have 10 bits which can be arbitrarily chosen, which means together we now have 20 bits of information which we can use to represent a certain character. Which means right now we can represent 1,112,000 different characters. And this is actually what defines the code range for Unicode. The Unicode spec says that any Unicode system should be able to at least represent this number of codes. But we can do even better than this. And this is where UTF-8 comes into play. UTF-8, famously invented on a written down on a napkin, is what is basically the holy grail of text encoding. ASCII, if you remember, only defines the first 128 characters, and remember how this made it so we have 1 bit to spare, and we can use this 1 bit to do a very clever trick, which allows us to differentiate multi-byte characters from single-byte character ones. So if we have a 0 followed by 7 other bits, we can just use the same encoding as ASCII. But if we have a 1 instead, we can actually use a number of following successive ones, followed by a 0 and then some bits, to indicate how many bytes this character is going to have. So 110 something something is going to be a 2-byte character. So this will be the first byte, and there will be one other byte that follows it. And then similarly, when we have 1110 something, then we will have a 3-byte character, which means we'll have 2 of these kind of bytes that follow it. And with this system, we can make characters bigger by just making this be more ones, and then we have more bytes to work with, which is very useful. UTF-8 only goes up to 4 bytes, but you can theoretically go up to 7 bytes in this case, which is, I don't know how much characters that would be able to represent from the top of my head, but that's this is already enough to cover the entire the entire Unicode spectrum. So this would be able to represent exactly 1,112,064 characters. And this format is even more compact than UTF-16, because the common characters in English, which is every character you see on screen right now, is compatible is in the ASCII table, which means that every character takes as much space as an ASCII character, and in fact is backwards compatible with the original ASCII encoding. And for this reason, everyone uses UTF-8 now. With a few exceptions, UTF-32 has from what I've understood, a few niche use cases, which you can basically forget. You can just forget UTF-32 exists after this talk. UTF-16 is still relevant. UTF-16 is used internally by Windows and is used in some other software, but it is slowly being phased out in favor of UTF-8. And ASCII is basically never used anymore, and except for people that use it, but those people just forgot to think. Okay, so let's go and talk about the last part of this talk. Floating point numbers. We were not done with numbers yet, and I've saved the best for last because this is actually a bit of a complicated topic. So right now we don't have a way to represent fractional numbers. We could just put a decimal in the middle, but you only need precision for small numbers and range and like the range for like big numbers. But those big numbers don't need to be very precise because they are big. They need at most to have like the same number of significant digits as a small number, but we give them way more if we have a fixed dot in the middle. So this is not a very efficient way to represent fractional numbers. So what will we do instead? Well, we look at a concept we probably learned in high school, which is scientific notation, where we will just write down a fractional number like this and then multiply it by a certain power of 2 or a certain power of 10. And we can use the same principle in binary when we create what is called a floating point number by taking our binary fraction and multiplying it by a certain power of 2. So we would have like 1 point something 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 times 2 to the power of negative 10, for example. And this is what the IEEE 754 standard does. This is the standard that is used in basically all computer systems right now. So we have first we start with a bit that represents a sign, which is just gonna say, is this number negative or positive, just like we would with our signed numbers. Then we have an exponent, which is the part you would see in the exponent right here. That's marked yellow here, and that will be 8 bits long for a 32-bit number. And then we have a fraction part, which is just gonna be the fraction right there. So in this case, it would be 1.283. That's gonna be the thing that's actually containing our specific number, and that's gonna decide mostly what the number is gonna be equal to. And we can therefore calculate our number with s times m times 2 to the power of e minus 127. So unlike how you might expect, this is not a signed number in the sense that we are used to. This is actually an unsigned number which is being offset by minus 127, which means it behaves a bit differently than what we're used to. I don't know why that is specifically, because I have not looked into the actual implementations of the IEEE standard. But there is probably a reason why they did it like this, because this was invented after signed numbers were a thing. There's also double precision floats, which are 64 bits, and these would have 1 bit, 11 bit, and 52 bits for the sign, exponent, and fraction respectively. There's also a few special numbers which we have to include. Due to the way we have implemented our sign and how we are representing 0, we actually have two zeros, -0 and 0, which are different in our number system. if you were to actually compare them on a computer, it will just say they are the same thing, so it will not cause any bugs. But they are in memory; they are represented differently, which is a interesting side effect. Um, we also have two infinities, which is when the exponent is equal to all ones. The computer interprets this as infinity, and that's for the reason that infinity is sometimes a useful thing to be able to represent. This is only when the fraction part is equal to 0. When the fraction part is not equal to 0, the computer will interpret this as not a number. And the reason for this is that there are actually multiple ways in which not a number can be created. And then in those cases, the mantissa actually contains some information about what went wrong in a calculation that caused this not a number to appear, from what I understood from the bunch of Wikipedia pages and YouTube videos that I did in my research. I don't know for certain if that's still used today, but it seems to be, because it's still part of the standard. And we also have subnormal numbers, which is basically when a number is so incredibly tiny that we we actually reach the smallest possible exponent, and we still need to, and our number would still be too big if we were to pad all the zeros out. So we would still, so our first two numbers, so our first few numbers would be zeros, basically, even though normally we would just pad those out, we have already reached the smallest possible exponent, so we are not able to do that, and that's why they call it subnormal. On that note, there's one thing which we still need to explain about this mantissa part. Because binary numbers, because we're working with binary numbers, we can actually use a very clever trick here. When you're working with decimal numbers and writing down a scientific notation, you want to have the first number in your fraction. You want that to be a non-zero number, because otherwise you can just remove the 0, then multiply everything by 10, and in this decrement the exponent by 1, and you would still have the same number in theory. But with binary, there is only one non-zero number, which is 1. So we can actually use one more bit to our advantage by just removing the first digit of our fraction altogether and just appending a 1 afterwards. And that's actually, this only contains the 0.15625 part. This does not contain this 0, basically. Or like in other way. So in this case, if we have this number, this is the part that is being stored, and this one is not part of the fraction, the blue fraction part. This one is appended in the conversion, basically, or it is implied, I should say. Binary floats have a few side effects when you're working with them. Because they are binary, and it is sometimes not possible to exactly represent a binary number or a floating point number, or a decimal floating point number in binary, because you would somehow end up with infinite repetition. It is the same concept when you are dividing 1 by 3. You would end up with 0.33333 repeating. Because we have no way to represent this fraction with a finite number of digits. And similarly, 0.1, I don't know if the 0.1 is one of those cases, but it probably is. You cannot represent it with a finite number of binary bits. It will have a repeating pattern going on infinitely. The same for 0.2. And when you add those together, you can get what's called a floating point error. And in some languages, this will cause 0.1 plus 0.2 to be not equal to 0.3, because this floating point error is causing some issues within this division. So exact equality checks against floating point numbers are in some languages not very reliable. And for this reason, some mathematically oriented languages use decimal form floating point numbers, which instead of using powers of 2, they will use the commonly used powers of 10, which makes decimal numbers when you're working with the decimal numbers, they will be exactly representable in your floating point. There is actually this very interesting video on a algorithm used in Craig 3, which calculates the fast integer square root, where people use the intricacies of floating point numbers to do a very clever trick to very efficiently and very effectively calculate a approximation of the inverse square root. If you're interested in that, you should definitely check it out. It talks about a lot of the same concepts I just explained. It's a very interesting video. And it's very, very educational. That's it for this talk. This was all I had in this was all I had in on the program for you today. So I hope you enjoyed this. Yeah. Are there any questions? Because I'll answer them right now. Hi. Yeah, the video is very good.
It's probably my favorite explanation of IEEE 754 that I've ever seen. It makes
Yeah,
absolute
he does it better than I did probably. But
Honestly, your explanation was also very solid. Thank you for having me.
thank you, thank you.
I really appreciate it.
Um, what is -0? Why is watching to my webcam? Let me just go and look up the bit representation of -0 so we can just see this. Let me just get one of these converters. So if we want to have 0 or binary bit representation, it's gonna be just all zeros. Yeah, that's I guess that's right. So this would be 0, but you have also this number, and this would also be 0, but those are two different bit representations for the same number, and that's why this is like sometimes referred to as -0. When you put these in, they will equal the same thing, but it's just a side effect of the standard. So yeah. Kind of like how there are equivalent real numbers. Yeah, I suppose, yeah. I think in most languages, in basically all major languages, the comparison between these two will match, because it would be very odd if for some reason these two you will end up with like -0 and 0. They have thought about this because these are the only two cases where this is a single case which you can just easily handle. You can just say like make an exception for when this is when you have all zeros like this, then the size should be ignored in the comparison. So in most major languages, I have not encountered a language which does not handle IEEE comparisons like that. They'll always return 0 when you're comparing 0 and against -0. But with that said, you shouldn't directly compare flows like that, because of the what is it called? Because of the floating point error I talked about. So 0.1 plus 0.2 will not always be 0.3 depending on what language and what kind of floating point you are using. It's becoming a new meme now. We're gonna have the division on this. We're gonna have like a political division in the server. The 0 against the -0. Oh God, it's happening. Yeah. Does anyone else have questions? All right. Well then, I'm gonna end um, the talk here, and I'll see you another time when I got some other topic I want to talk about with you guys. All right. Thank you for listening, and I'll see you another time. Probably next video if that's something you can count. Bye bye.